Dear all, now I am going to take data path and control considerations in this video lecture. Before going to that, we have to see little bit about buses, standard I/O interface, pipelining, influence on instruction sets, and then superscalar operation. So first, in case of standard I/O interface, we have three major standard I/O interfaces. Number one, peripheral component interconnect. So PCI in short form. Small computer system interface. SCSI. Universal Serial Bus. USB. First, PCI bus. So the structure is first one host. Host is nothing but a computer only, and it will be starting computer. I think it may be called as master also. And then main memory. Those two are connected with PCI bridge through which PCI is connected. PCI bus is connected, and this PCI bus is used to give connection between the devices at the other end and host computer. So in the other end, we can have I/O devices, namely disk, printer, Ethernet interface. So host computer through PCI bus, it will be connected to disk, printer, Ethernet surface, and so on. So many devices can be connected. So the host, it is along with the main memory and PCI bridge are connected to disk, printer, and Ethernet interface through PCI bus, as we have seen in the previous diagram. At any given time, one device is the bus master initiator. So here the host is master or initiator. It has the right to initiate data transfers by issuing read or write commands. A master is called an initiator in PCI terminology. So starting, which one starts connection request, that device is known as host. And this is either processor. So the host is generally computer or processor or DMA controller. The addressed device that responds to read and write commands is called a target. So the host is willing to have a connection to the either print or disk, which are connected at the other side of the PCI bridge, PCI bus. So those devices will have their own addresses. So if the addresses will be called by the host, then identifying that address, I mean the recognizing those addresses, the respective devices will be responded to read or write operation or else commands. So those devices are called, that means addressed devices are called target. A complete transfer operation on the bus involving an address, a burst of data is called transaction. So before data transfer, the host must address the device by sending the address, and then after responding to, the devices will have the transfer of the data. So data means here not a single bit, it is a block of data, group of data. So this is known as the transaction. The device configuration, how it is made. PCI bus is a good example. That means low cost. So most commonly used system bus. It supports the functions found on a processor bus bit in a standardized format that is independent of any processor. That is why we are adopting PCI bus. It is low cost and most frequently used. But what is the reason behind it? Every computer, every processor will have their own architecture, but all are supported by the PCI bus. That is why independent of any particular processor, whatever the type of the processor may be, the PCI can be adaptable. Devices connected to the PCI bus appear to the processor. So this is important. When through PCI the devices are connected to the processor, then it will have the feeling that the devices are connected to the processor directly, but actually they are not connected to the processor directly, through PCI bus only. So this is the another reason why PCI bus is used in general. So as if they were connected directly to the processor bus. They are assigned addresses in the memory address space of the processor. So all the devices, every device's address will be stored in the address space of the processor. PCI follows a sequence of bus standards that were used primarily in IBM PCs. So the PCI bus is following the bus standards which is adapted. I mean, it is internationally accepted. So accepted means primarily it is used in IBM PCs, and early PCs used the 8-bit XG bus, whose signals closely mimicked those of the Intel 8086 processors. So previously it has resembled the 8086 processors. Nowadays it is IBM, similar to IBM PCs. Later, so previously 8-bit, later 16-bit bus used in the PCAT computers. These AT computers are nowadays used in the embedded system, Arduino board, IoT systems, became known as the ISA bus. It is extended 32-bit version is known as EISA bus. Other buses with similar capabilities are the micro channel used in IBM PCs and new bus which is used in Macintosh computers. Its design anticipated a rapidly growing demand. So they are all improving. They are all improved as days move on. For the bus bandwidth, because nowadays we are using superscalar operation and multiple computers, so automatically we are in need of the bus bandwidth to be exaggerated. So if we are increasing the bus bandwidth, then automatically it should be supported by the bus. That is why bus bandwidth to support high speed disks and graphic and video devices, as well as the specialized needs of the multiprocessor systems. An important feature that PCI pioneered is a plug and play capability for connecting IO devices. This plug and play capability is nothing but one feature, and what is that feature, how it is used, how it is functioning, that we we will see later in the slides. And to connect a new device, the user simply connects the device interface board to the bus. So it is well known that nowadays in IoT also there will not be direct connection because of the voltage difference, because of the voltage difference, speed difference. In between, the interface circuits will be used. So that is mentioned here. Nowadays, if you want to connect a new device, because already which are the devices to be connected to the host, those addresses will be stored in the memory of the processor. But new devices have to be connected to newly they have to be connected, means we can no need to connect them directly to the processor. In support with the interface, we can add the new devices to the processor. The software takes care of the rest. And then how the data transfer occurs. Most memory transfers involve a burst of data rather than just one word, one bit by one bit, or one word by one word. Not like that. A block of data is transferred because to increase the speed of the operation. And the reason is that modern processors include cache memory. So increase speed means cache memory always it is fast. So the speed has to be managed, and the data are transferred between cache and main memory in bursts of several words each. So a group of data will be transferred from cache to main memory, or from main memory to cache, both way transactions. The words involved in such a transfer are stored at successive memory location. So this is the point to be noted. If a block of data is transferred, the starting address is necessary, because while initiated by the processor will give the starting address of the block. So once if it is initiated, the processor will go out to perform other operations. So from the starting address, one by one consequent addresses will be allowed. Then when the processor specifies an address and requests a read operation from the main memory, the main memory responds by sending a sequence of data words starting at that particular address. So what are the address mentioned by the process? From that it will send the data. So for the read operation it is given. And then during a write operation, the same thing, from which main memory location the data are to be written, the starting address will be given as in the case of read operation. During the read operation, the processor sends a memory address followed by sequence of data words to be written in successive memory location. So starting address only it will give, and then data will be given. So from the starting address, the data will be stored sequentially. The PCI is designed primarily to support this mode of operation. So block of data transfer, either read operation or write operation. Read or write operation involving single word is simply treated as, so it will be mentioned in the books as a single word transfer, a single transfer, like that. But we have to understand that single transfer means single block of data transfer. If the bus supports three independent address spaces, first one memory address space, IO address space, configuration address space. So the bus, because in the processor there are three address spaces with what devices are to be contacted with, those are called as IO, external peripheral devices, IO devices. So corresponding devices addresses will be stored. In the same way, memory address, main memory addresses, and the configuration of the devices. For the configuration, why this address of the configuration is given, I will tell you in the next slide. The first two are self-explanatory because we know about the main memory, we know about the IO devices. IO address space is intended for use with the processors such as Pentium that have separate IO address space. So if you take a Pentium processor, there will be separate address space for storing the IO devices address. However, but the system designer may choose to use memory mapped IO. So even though it has IO address space separately, it can follow the concept of memory mapped IO also. What is memory mapped IO? The address will be common for memory as well as IO. So this concept also may be followed. It is not a constriction. And then, in fact, this is the approach recommended by the PCI. It's plug and play capability. A 4-bit command that accompanies. So, which address space is to be used, that will be indicated by using a 4-bit command. So, identifies which of these spaces is being used in a given data transfer operation. So first, 4-bit command will be sent. It is indicating that which address space will be used. The address is needed only long enough for the slave to be selected. So address, what for the address is given. Normally I told the host PC is initiator and it may be called as master, and then the other devices will be called as whom it is controlling. The master is controlling means the remaining devices are called as slaves. So as long as master wants to have a read operation means read or write operation means it has to send the address of the slaves. So the address will be available how long? As long as it is received by the slave and it is responded to. Up to that time, the address will be available or stored. Thus, the slave can store the addresses in its internal buffer. So its address will be stored in its internal buffer. Then only it can identify. Thus, the address is needed on the bus for one clock cycle only. So normally in processors, for one clock cycle, one operation will be completed. In the same way, sending the request and responding by the slaves will be occurring during only one clock cycle. So the slave respond to the address within the one clock cycle, freeing the address line to be used for. So in one clock cycle, the address will be available in the bus. During that, the addressed slave will be responded to. After that, after responding, the address is no more necessary. So the address bus will be released for the further operation and to be used by the other devices. The result is a significant cost reduction because the number of wires on a bus is an important cost factor. This approach is used in the PCI bus. Next one, device configuration. When an IO device is connected to a computer, several operations are needed to configure both the device and software. that communicates to the processor. The PCI simplifies this processor by incorporating in each IO device interface a small configuration ROM memory that stores the information about the device. So, what the statement conveys, each and every IO device will have separate memory space which is called as ROM memory, read-only memory. Thus, the read-only memory ROM contains the configuration of that particular IO device, and then the configuration ROM of all devices accessible in the configuration address space. So these will be stored in the configuration address space. Already we had seen in the previous slide, I told you three address spaces: memory, IO and configuration space. I told you what for this configuration space and how it is used, what purpose it is used. So now the result is, the answer is given. So each and every IO device will have its own ROM. This ROM is storing the configuration details of that particular device, and the address of this ROM will be stored in the configuration space. PCI initialization software reads these ROMs whenever the system is powered up or reset. So PCI knows when to read this configuration. Whenever it is necessary, it will access the ROM to know the configuration and address of the device, IO device. In each case, it determines whether the device is printer, keyboard or Ethernet interface or disk controller. Whatever the devices it may be, it will be identified by the PCI. So it can further learn about various device options and characteristics. Devices are assigned addresses during the initialization process. And then here one more point we need to note down, during the initialization process, because one processor may be connected to several devices, but no need to say all devices will have the connection to the main host computer. Actually, the devices are assigned addresses during the initial. So for after initialization only, the devices will have contact with the, connection with the main processor. So for this initialization, the device will send, because that device has to be selected. So one signal IDSEL, that signal will be sent by the device. Then only the host will contact with the device. So n number of devices will be connected, but all n number of devices will not have contact with the connection with the main host computer. So only thing, once in the initialization, whatever the devices are addressed, those devices will have the connection with the main processor. So this means that during the bus configuration operation, devices cannot be accessed based on their address, as they have not yet been assigned one, because they are not one, they are multiple devices, so they don't have access. Hence, the configuration address space uses a different mechanism. What is that mechanism? Each device has an input signal called initialization device select IDSCL. So after getting this signal only, the device will be responded by the main processor. The next one, SCSI bus. SCSI bus is used to connect and communicate between computers or servers and peripheral devices. So external devices such as hard disk drives, that means external memory devices, hard tape drives, CD or DVD drives, and scanners, printers, and so on. There are several components used in SCSI storage system. So it is also a bus, but this bus is having so many components. What are the components inside this SCSI bus? Number one, initiator. So initiator we know. It initiator issues request. So initiator available in SCSI bus should initiate the request for service by the SCSC device and receives responses to which device it is giving the request. That particular device will give the acknowledgement and that response is taken by the SCSI bus. Initiator come in a variety of forms and may be integrated into server's system board or exist within the host. So it is available inside the bus within the host bus adapter. Internet SCSI also available. This connectivity uses software based initiator. Previously this is hardware initiator. Software initiator is used in internet SCSI. And second component available in SCSI is controller, also known as host adapter. The SCSI controller coordinates the activities between computer and the devices connected to it through the SCSI bus, and it is available in the shape of a slot, as a card, or inbuilt. Inbuilt means it is built into the computer's motherboard itself. And the third component is target. SCSI target is typically a physical storage device. It is bus only. It is carrying the information or data as well as it is storage device. Although software based SCSI target also exists. So in the previous slide we have seen ISCSI, Internet SCSI has the software. Okay, software target. The target can be a single hard disk or an entire storage array. So already we told that it is a storage device only. So the target can be single hard disk or a large memory storage array. It is also possible for non-storage hardware also to function as a SCSI target. Although rare today, it was once common for optical. This non-storage hardware will be used along with the optical scanners because the data will be flowing so fast so that no need to store intermediately. So in that case, the software target will be used. So in the optical cases, software target will be used. And then fourth one, service delivery subsystem. So service delivery, we know the it has to have a smooth transport of the data. This component is a mechanism that enables communication to occur between the initiator and the target. Usually takes the form of cable. So through cable it is happening. And then fifth one, expander. Expanders are only used with the serial attached SCSI. This is in the short form SAI to enable multiple. So expander means it is for multiple SAS or to share the single initiator port. So one initiator, multiple target. For that purpose, this expander will be used. And then cable. The internal devices connect to ASC controller with the ribbon cable. So this means that inside the system, what are the components available? They will have the connection through the ribbon cable. If suppose outside, then the cable will be daisy chain. Next one, so after this we have seen in general how it is written. It is host bus in one side CPU. It is connected with the CPU, main memory and other module, internal modules. And then through SCSI controller, SCSI bus through which there may be larger number of disks may be connected. And then third one, universal serial bus USB has been designed to meet several key objects such as first one, provide a simple, low cost, easy to use interconnection system that overcomes the difficulties due to the limited number of IO ports available on a computer. So nowadays we are using USB. So we all are using USB because there are minimum number of IO ports available in the computer. Accommodate a wide range of data transfer characteristics for IO devices including. So normally for communication, USB plays an important role. Enhance user convenience. It is user friendly through plug and play mode of operation. Next one, port limitation. So how to overcome this port limitation? By using USB. To add new ports, user must open the computer box to gain access to the internal expansion bus and install a new interface card. So to increase new ports, to expand the number of new ports, we have to open the computer box. The user may also need to know how to configure the device and the software. That is obvious. It is possible to add many devices to a computer system at any time without opening. So with the opening the box means we have to increasing the number of ports. Without opening the computer means we can add the number of devices. So this device characteristics, the kind of devices that may be connected to a computer cover a wide range of functionality. So what are the functionality? Number one, speed. So devices and processors means, so devices means IO peripherals that they differ completely from the processor. So the main characteristics to be considered are first one, speed, volume and timing constraints, and second one, variety of simple devices attached to a computer generate data in different asynchronous mode. That means with different speed they will allow the data to flow, so to come in, to go out, both ways the data speed will be different for different devices. A signal must be sampled quickly enough to track the highest frequency components. Next one, plug and play. So in several places we have seen the features of plug and play, and I told you that what is plug and play. So if whenever the device is introduced, a new device is getting connection with the main processor, we should not turn the computer immediately off or press the reset button. So we should not do. We should come out, log out, and then make the system shut down to connect or disconnect the device. The system should detect the existence of this new device automatically. So we should not abruptly switch off the system and make the device getting connected with the system. If it is new device is coming in, that should be identified by the identified by the processor automatically without a reset, without a restart. Now USB architecture, how it is provided to accommodate larger number of devices that can be added or removed. So till now we have talked about the adding of the ports or adding of the devices, but removal is also possible at any time if we are using the USB in the tree structure. Tree structure. Each node has a device called a hub. So every division part, if one is divided into multiple, that multiple branch at the extreme edge, it will have one computer. That computer is nothing but a connection contact, and it is called as a hub. And then the main starting initiator is called as root hub, and functions split bus. It will have the operations, namely high speed and full or low speed. These two are the features available in the split bus operation. Next one, see, this is the first computer. So starting initiator, that is why it is named as root hub, and it is divided into many hubs, subdivisions. Here two hubs are indicated, and from this hub one more hub, and the second one no need to have the hub only. Hub means it is the computer, but it may not be a computer, it may be IO device also. And then this hub, and here one hub is divided into branches, one hub branches to another hub and IO device. Not only the case, it will have two IO device also. It may have the branches to two IO devices also. See, first one root hub is divided into two hub only. It branches to two hub only, and one hub branches to one IO, one hub, and this hub branches to two IO. In the same way, this hub branches to IO device means not only one or two, many IO devices. That is why here there is a difference in indication. Three IO devices will be connected. And then host computer, it is root hub based on the operation. In the previous slide we have seen high speed or full speed or low speed. So in case of high speed, there are two hubs connected. Both branches are with high speed operation, means one is hub A and another one is hub B. And this hub, suppose if it branches to high speed and full or low speed, then it will go to the different devices which are working with a different speed of operation. So if it is of top priority and high speed, then hexes will hexes will move to the device C. Suppose device D is operating with very low speed, then the operation with this branch will be having full or low speed. So it is categorized based on the operation with which it is transferring the data. Next one, influence on the instruction sets. First one, pipelining. It's a technique that overlaps. So normally for the pipeline, we have to segregate one instruction into so many phases, so many subtasks. Normally 4 subtasks or subtasks. So in this way, every upcoming instructions will be divided into 5. 4 means uniform 4. 4 means uniformly 4. 5 means all instructions uniformly 5. Why we are dividing into subtasks? In one clock cycle, we know that one operation will be completed. But if it is so for all subtasks, we need so many clock cycles. So what we are doing, since the phases are different during one clock, for all instruction, different subtasks will be worked out. If it is done like this, there will not be any overlapping of the results. The results will be correct. So that is the pipeline. So it is that involves overlapping of execution of multiple instructions. So how we will overlap significantly influences the instruction set designed by favoring set designed by favoring instruction sets that are simpler and more regular, thus enabling more efficient pipelining. And one more restriction is there: we cannot apply this pipelining concept for all instructions. Only simpler instructions on which we can apply this pipelining concept. This is because simpler instruction sets are easier to break down into a fixed number of pipeline stages. They are uniform, so that we can uniformly split up into many stages and can be executed more quickly, leading to high throughput. High throughput means high performance. Efficiency will be increased. And then first one, simpler instruction sets are easier to pipeline. Pipelining involves dividing the instruction execution into multiple stages, each performing a specific task. They are unrelated to one another. If the instruction is divided into 4 stages, 4 stages are independent of one another. If 5 stages means 5 are independent of one another. Simpler instruction sets with fewer operations and more straightforward structure are easier to divide it into these stages. These instructions we can divide into multiple stages. This makes the pipeline design simpler and less complex, leading to faster execution and higher performance. Second one, regular instruction formats are crucial for pipelining efficiency. First one, a consistent and predictable instruction format allows for efficient pipelining. So, it should not be random. The instruction sets should be understandable and predictable and known to all. So, the format should be known. The instructions with varying length. So already that is why I am telling uniform, that word I am using. So with varied length or complex format can disrupt the smooth flow of instruction through the pipeline, potentially leading to, so pipeline why we are using to increase the performance. So if any disturbance occur to the pipelining operation, then automatically the performance will come down. How the disturbance will happen? The instruction sets are not uniform. The flow of data is not smooth. So that time the pipelining will not be performed correctly. So that the performance of the system will come down. Next one, risk-like instruction sets are often preferred for pipelining. So, what is the solution? So non-uniform means the pipelining will not be handled properly. So we have to give solution. What solution? The instruction sets should be in a standard format. It should be understandable. That is why risk processes we are undertaking, risk reduced instruction set computer. This architecture is known for their simple and regular instruction sets which are well suited for pipelining. So, in risk processor, the most welcome concept is pipelining. In contrast, CISC, complex instruction set computer, CISC architecture can have wider range of complex instruction which can be harder to handle the pipelining efficiently. The increased throughput and cycle time reduction. Throughput, we know that throughput means it is performance efficiency. But what is cycle time? In the previous videos I told, cycle time means after first one clock cycle is sent, during that some specific task is completed, after that second clock cycle will be sent. The time delay between the starting of the first clock cycle and the second clock cycle is known as the cycle time. This cycle time should be reduced because one clock cycle means immediately after completion of the one duration. One clock cycle means one unit time. Within that, the task should be completed immediately without any delay. The second clock cycle should start. Otherwise, cycle time will be more. We have to, our ultimate aim is to reduce the cycle time. That is why both coming in the same statement, increased throughput and cycle time reduction. Pipelining allows multiple instructions to be processed simultaneously. Thus, we are increasing the throughput, overall throughput. And then it also reduces the processor cycle time. So, time between clock leaves leading to faster execution. So next one, pipelining hazards. So pipelining, when we are handling the pipelining, we have to face hazards. What are the names? The types of hazards are, first one, data hazards. Data hazards means, suppose first instruction performing add operation. The result of the add operation is given as the input to the second instruction, means the first instruction should be executed in correct time and it should supply the result to the second instruction as input as early as possible. Suppose the addition is performed with the delayed manner, the data available for input will be some other input and not the output of the first instruction. That is the data dependency between two instructions. And suppose if it goes wrong, then it is named as data hazard. See, the dependence of the results of the previous instruction. And second one, branch hazards. Suppose if condition, otherwise subroutine occurs, go to some other, suppose the controller branches to some other memory location for performing subroutine task, interrupt task, then it is known as branch hazard. Then structural hazard, insufficiency of the resources for the pipelining operation. When the task is performed, the available resources are not sufficient, means it is known as structural hazards. Next one, instruction set design can influence the severity of these hazards. So already it is unavoidable hazards are there, but the instruction sets the form of instruction sets will severely affect, and these three hazards will be present more seriously, and the technique used to mitigate them. Pipelining favors simple, more regular instruction sets that are easier to break down into simpler stages. So, to avoid the severity of these hazards, we have to follow these instructions in advance for preparing the pipelining operation. So if we are cautious in selecting this type of instruction, then it will lead to improved performance in terms of throughput and reduced clock cycle time. This has influenced the design of modern processes, especially risk only. So risk only is applying the pipelining process, often being favored for their compatibility with the pipelining technique. So already they are manufactured with the compatibility of the usage of pipelining concept. And then data path. So after seeing this, what considerations we have to have data path and data control consideration. Data path, already from the name itself you can understand the meaning, the correct flow of data. And then the controlling of the operation should be correct. The direction of the flow of data should be correct for read or write operation. That is the data path and control consideration. Pipelining in computer organization involves dividing instruction. Already we know execution into multiple stages to allow overlapping execution, improving throughput. This requires careful consideration of both data path. So data path means hardware, because the buses through which the data is flowing, and the control unit. So control means, suppose in the program we do have if else condition or branch condition. Those are the control instructions through which the structural hazards and control hazards will happen, branch hazards will happen. That is why this should be taken care of. Using the control branch instructions should be taken care of very seriously. That is known as software software data path. The data path needs to be structured to handle multiple instructions concurrently. So first instruction output is going to second instruction input. So that is the multiple instruction, handling of the multiple. The flow of data within the instructions should be done correctly, concurrently, and control unit needs to manage the flow of instructions through the pipeline. It has to manage everything. And data path considerations in this case, what are the pipeline stages? The data path is divided into stages like so. It is depending on the architectural structure, either 4 stages or 5 stages. Now here instruction fetch number 1, IF, decode instruction decode second one, execution EX third one, memory access MEM, and fifth one write back. So in this write back the results are written, and this memory MEM, why this MEM is used? Since we are using the multiple stages, in between the 2 stages we used to have a small memory storage for holding the data from out to input. That's all. It will not do any variation on the data. It will not have any affect in the data. It will not do any, it will not have any effect on the data. It has to hold the data for a fraction of time before sending to the next stage. So this is MEM. It is only storing the data. That holding, not storing. It is holding the data from output to input. So pipeline registers. These are placed in between stages to hold the instruction for either memory or register or buffer or flip-flop, whatever it may be, or delayed element, whatever it may be. So some cases registers may be used to hold the instruction state as it progresses through the pipelining, allowing subsequent instructions to begin execution before the previous one complete. Suppose it will be preventing the errors happening, because whenever the data dependency comes and second stage is expecting the output results from the first stage, if this register is present at that time, it will have some delay to the second, it will supply some delay to the second register before getting the output from the first one. So up to that time, the second block will be waiting. That is what the meaning, allowing subsequent instruction to begin execution before the previous one is complete. Before the previous one is complete. And then hardware duplication to allow multiple instructions to execute concurrently, simultaneously. Hardware elements like ALU, register files, and buses needed to duplicated or shared between stages. So these are all. Once shared bus means it is duplicate only. In the same way, once if ALU is shared between two processors, then it is duplicate. Then data transfer. Data need to be transferred efficiently between the stages, often using dedicated buses for data transfer and dedicated bus for control signal to manage the data flow direction. And then functional units. Each stage may have its own dedicated functional unit like ALU for execution stage or memory access unit for the memory stage. And then control consideration. So up to this data path consideration. Now coming to the control consideration, instruction sequencing. The control unit determines the order in which the instructions are to be supplied, are to be taken, and then decoding, and then execution, and then writing the results. All these ensure the correct execution flow through the pipeline. And then control signal. They are used to manage the data flow, ALU operation, and memory access, ensuring the data path functioning correctly. And then hazards. So pipelining can introduce hazards. As we have seen already, data has, control has, structural hazard. That require careful handling to prevent incorrect execution. So ultimately, we are expecting the correct result, the correct output. There should not be any errors in the output. Hazard handling techniques. What are they? Techniques like stalling. Stalling is nothing but a delaying. So in the previous slide, I told you. So suppose the first instruction is not executing in correct time. It is just delaying in between one unit, memory or delay unit. It is useful for preventing the useful to prevent the wrong execution, because correct output should be given as input to the second unit. So that is stalling. Delaying means stalling. Next, forwarding. So correct data forwarding and branch prediction. So it is already anticipated. The branch instruction will come. It is known advanced, are used to mitigate hazards and maintain the correct pipeline operation. Second one, pipeline management. How it is managed? Using the control unit only. It has to manage the pipeline, including filling. Including filling means every stage is to be filled with the pipeline. Okay. Emptying. Suppose if the operation is completed, execution is over, those should be emptied. So it has to give the way to the next instruction and maintaining the correct sequence of instruction. So filling, emptying, and flow of correct instruction. In essence, the data path provides the hardware infrastructure for pipelining. Hardware infrastructure should be correct for the pipelining, ensuring efficient and correct execution of the instruction. So incorrect should not happen. Anyway, the mistake should not happen. So after this, we have to see about the superscalar instruction, superscalar operation. So pipelining, multiple processors. These are all the basic for learning the superscalar operation. So a more aggressive approach is to equip the processor with multiple processing unit to handle several instructions in parallel in each processing stage. So in the previous case, we have divided the instruction into so many stages, but here so many processors, that is multiple processing unit means so many processing elements, PEs, processing elements are used. With this arrangement, several instructions start execution in the same clock cycle. Previous case, in one clock cycle, various instructions, various stages of various instructions. But here, in the same clock cycle, and the process is set to use multiple issue. So same clock cycle, since we have multiple processing element, multiple instruction. See, this instruction is named as issue here because supplied with, that is why multiple issue. Such processors are capable of achieving an instruction execution throughput of more than one instruction per cycle. More than one. So normally one clock cycle means one task, one instruction. But here we have so many n number of processing element means n number of instructions will be executed in one clock cycle. Therefore, throughput is equal to n into, so n number of multiple times throughput we are achieving. They are known as superscalar processors. And the superscalar processor structure is, so normally in the computer architecture till now we are considering the integer operation only. For integer operation, one unit is enough. For doing floating number operation, we need to have separate unit. So integer, normally the integer unit will be in operation always. So if the scenario is coming under the floating point unit, that time only floating point unit will become operating. So here F is instruction fetch unit. So here instruction queue, and then dispatch unit here it is going to floating point unit or integer unit. Normally it will go to integer unit only. Suppose the operation is based on floating point unit, then it will be supplied to the floating point unit. And then floating point unit output, integer point unit output will be differently supplied to the right results. So a processor with two execution units, two processing elements, two executing elements. So in the above diagram, there is a processor with two processing elements. That means two execution units, one for integer operation and another for floating point operation. The instruction fetch unit is capable of reading the instruction at a time and storing them in the instruction queue. So in the instruction queue, there are separations in each and every partition. It's multiple instructions will be stored. I mean, it is they are waiting in the queue, and in each cycle, the dispatch unit retrieves and decodes. So one by one, the dispatch unit takes in and then decodes the instruction from the front part of the queue. So in the queue means from the front part only it will take one by one, not randomly or not from the other end. If there is one integer, one floating point instruction and no hazards, both the instructions are dispatched in the same clock cycle. So one integer instruction, one floating point instruction means, and instructions are independent instruction. It may not depend on the results from the another instruction. Then we may say that there is no hazard, no instruction hazard, no data hazard. So we can expect this smooth operation. At that time, the dispatch unit will do the two operations in one clock cycle. What are the two operations? Number one, floating point, number two, integer point. So advantage of this superscalar architecture is the compiler can avoid many hazards through judicious selection and ordering of the instructions. So the instructions are arranged in queue one by one, and the operation is also performed from the one end of the queue, not from the another end. So it is totally avoiding the hazards. That is the main advantage of the superscalar architecture. So dear friends, with this I conclude this lecture. We will see in the next video. Thank you.